Hello everyone, my name is Lionel Rieg and I'm going to present our work about computer-assisted design of a query by construction algorithm for robotic swarms. Why do we consider swarms of mobile robots? In a harsh environment, a robot may fail. So if you send a single one, then you'll have a complete failure of your mission. Whereas if you send a whole flock of them, it may recover from the failure of some robots. As some will fail, you want them to be cheap, which means they only have weak capabilities. But despite these weak capabilities, you still want to be able to tackle life-critical missions with the highest level of assurance, which in our case means using formal method, in particular the cock-proof assistant. I want to focus on the Lifeline problem, which aims at preserving connection between a fixed base and a moving scout. But unlike a theoretical study in which you want to know precisely under which condition the problem may or may not be solvable, here I'm more interested in getting a realistic solution from an implementation perspective, but still using formal methods to ensure the highest level of correctness. So let me describe what this Lifeline problem is. We initially have a fixed base on the scout, and the scout moves in space. At some point, it may reach the transmission range of the base on the scout, and to be able to move further away, we need a way to forward communication. We do that by using mobile relays that will serve precisely as transmitter between base and the scout. And as the scout moves, so does the relay, but at some point, in order to move further, you'll need to introduce a second one, and so on and so forth. And the environment you want to preserve is that there is always a path of connection that links the base to the scout. The formal setting that we use to describe this problem is the one introduced in the seminal paper by Suzuki and Yamashita in 1999, in which robots are identical, anonymous, and don't have any memory. And they work by performing the look, compute, move cycle. So first they look at the surrounding and take a snapshot. Using this information, they compute some action to perform, usually to move to some specific point. And in the move phase, they finally move toward the destination. There are also various variants depending on whether we want on the type of fault we want to consider and the type of synchronization or adversary. In our case, the properties for the Lifeline problem we want is first that there is never a collision between either relay robots or a relay and the scout, and also that there is always a connection path between the base and the scout. For the absence of collision, it's easy to formalize. We can just say that for any two robots, R and R prime, if they are different, then their locations are also different. The specification for the existence of a connection path will come later according to our methodology. So the idea here is to have a co-design of the algorithm and its correctness proof by iterative refinement, building on the cock-proof assistant and the Pactole library. So for instance, if we have a line of robots, then we don't know in which direction the scout lies. So for instance, we don't know whether we should follow the robot in front or the robot in the back. To be able to solve this issue, we introduce identifiers, so robots are no longer anonymous, and in particular, the scout and the lower the identifier, the closer we are to the scout, and in particular, the scout has the minimal identifier 0. In order to make sure to avoid collisions, at some point robots may need to withdraw to eliminate themselves to make sure that there is no collision between either relays or a relay and the scout. But when you introduce this idea of removing robots from the algorithm, then you have issues with maintaining connection. And to solve that, the robot must warn their neighbors they may need to withdraw, and so that preserving the connection should be done without taking them into account. And so there is a form of communication with the so-called luminous variant of the Suzuki and Yamashita model. Overall, we use the look, compute, move cycles with identifier communication using light. Describing that there is a connection between the base and the scout is decomposed in two properties. First, that there is a path from any robot to the scout, and then that there is always a robot close to the base. And having a path from any robot to the scout can be easily described as, for any robot R, if the robot is live, then either it's the scout, or there is another robot R prime, which is also alive, which has a smaller identifier, meaning that it's closer to the scout, and which is still in range of R. This specification and the associated proofs are done with Pactole, which is a formal library for for modeling robotic swarms on top of the cockproof assistant. Using this library, you have a single framework in which you can express everything. So first, the specification can be done in a language which is very close to what we have in papers, very close to math, and we can perform both proof of correctness of algorithm, impossibility of solving a problem in a given model, or even compare the expressive power of various models. Thanks for watching.